All right, in this question, it shows you a diagram, the part of the graph of y equals to x squared, okay, a graph that you're quite familiar with rectangles approximating the area under the curve between the limits of x equals 0 and x equals to 1. Prove that the total area of the four rectangles shown may be expressed as this particular expression. So you notice that summation becomes one of the prerequisites that you need to have. This is in chapter 2. All right, but you need to prove that this total area can be expressed as this. All right, the expression is given, the graph is given for you here. All right, so this is the first requirement of the question. Number 2, in general, when the x-axis between x equals 0 and x equals to 1 is divided into n equal parts, okay, meaning from 0 to 1, now I'm going to divide it and I have n equal parts. Now, what does that mean? If there are n equal parts, means the whole uh, the the whole interval of 1 unit is now divided into n parts of equal width. And how do I find that? It will be 1 minus 0 divided by n. That means each width is going to be 1 over n. We're going to see how this impacts the interval later on. But, well, the area under the curve may be approximated by the total area A of n minus 1 rectangles, which is what you are seeing here in the previous part of the question, right? If you remember, uh, if you look at this the axis over here, the x-axis, there are actually 5 equal parts. 1/5, 1/5, 1/5, 1/5, 1/5. 5 equal parts, but 4 rectangles. Now, n equal parts, n minus 1 rectangle. So actually there is some similarity between these two questions, right? Each of width 1 over n. So this is how 1 over n came about. Right? Now, given that summation of r equals to 1 to n of r squared is this, so this is a given expression, show that the area A can be expressed as this. So this is the second requirement. You are then asked to explain briefly how the exact value of this integral can be deduced from this expression. So that is the third requirement. And lastly, why the definite integral 0 to 1 x squared dx is larger than this expression that you are seeing here. Okay, not a very simple one for the fourth requirement. So let's see how we can deal with the first one. Right, let's begin. Now, the four rectangles, okay, have width 1/5 given in diagram, and because you want area of rectangles, right, you need a height. So the heights are of, so how do we find the height? Now notice that this point here lies on the graph, right? So this is a point 1/5, and what is the height here? The height is given by the y coordinate of the graph. So this is actually 1/5 squared. So now the second coordinate, this is 2/5, and the y coordinate is actually 2/5 squared. Similarly, this point is 3/5, 3/5 square, and the last rectangle here is 4/5, 4/5 squared. So the heights of these rectangles will then be 1/5 square, 2/5 square, 3/5 square, and 4/5 square, respectively. All right. Therefore, the area of the four rectangles are area of rectangles width times length times breadth, right? Height times breadth, right? So it's the width is 1/5 times 1/5 square. Next one is 1/5 times 2/5 square. Now, why is that so? If you look at the axis again, each of it has an equal width of 1/5. Right? So it's length times breadth, length times breadth, length times breadth, length times breadth. Okay, so this is 1/5 times 3/5 square plus 1/5 times 4/5 square. Okay, now remember the question asks you to prove 1 over 5 cubed sum of r squared r equals to 1 to 4, right? So where does this come about? So we can factorize 1/5 first. So this becomes 1/5 square plus 2/5 square plus 3/5 square plus 4/5 square. By summation, you know that you can rewrite the sum in the parentheses. This becomes 1 over 5, right? Let's take a look. The ones that are changing are the numerators. So I can rewrite it as the sum, right, of everything over 5 square, right? And the numerator becomes r. This is r equals to 1 to 4. Okay, you can expand this sum to see that it tallies with what you have seen earlier on. All right, and this becomes 1/5. The sum of r equals 1 to 4, 1/5 square times r square. Or okay, maybe a simpler way to write this would be r square over 5 square. And that becomes 1 over 5 cubed because constants can be factorized out of the sum. R equals 1 to 4 of r square. And this is shown. Okay, simple. That is part 1 of the question. Next, remember they say that now the axis is split into n equal parts, all right, with n minus 1 rectangles, each with 1 over n. Now, why is this information important? Because it's trying to tell you that the rectangles formed in this paragraph is similar in scenario to what you see earlier on. So in part 2 of the question, for a better understanding, and it's going to be essential for you later on, it is for us to draw a diagram, all right, with n equal parts from 0 to 1. So how are we going to go about drawing this? Remember, each of with 1 over n, meaning 1 over n is here, 2 over n, 3 over n, and n minus 1 over n, this is n over n. Yeah, this is equals to 1. This is y equals to x squared. Now, what do I mean the rectangles are similar to what you see in the given diagram? Notice that the rectangles are all left bound. That means the height of the rectangles are all taken from the left hand side. Therefore, if you start from 0, okay, there's no rectangles here because the height is 0. And similarly for the one where you have 5 equal parts, the first height that you see is actually 0. Therefore, out of n equal parts, you only get n minus 1 rectangle. So the first rectangle to see is actually from x goes to 1 over n. Right? So this is actually 1 over n squared. The second rectangle, left bound, taken with x value 2 over n, has height 2 over n squared. And so on and so forth. So make things clearer, I'm going to draw the one before, n minus 2 over n, left bound. This is n minus 2 over n minus 2 over n squared. And the last rectangle you're going to see is n minus 1 over n minus 1 over n squared. So these are the n minus 1 rectangles you're going to see. Right? And we are ready to start the next question because the question at the end says, all right, show that A, the area of the n minus rectangle, can be written as this, right? So we need to know how to calculate the area of rectangles, which is given by the diagram. Okay, so from the diagram above, all right, when the area is divided into n equal parts, okay, the area of the n minus 1 rectangles, A, is given by 1 over n times 1 over n squared plus 1 over n times 2 over n squared plus 1 over n times 3 over n squared, so on and so forth until you have 1 over n times n minus 2 over n square plus 1 over n times n minus 1 over n square. What does all this mean? I can have 1 over n multiplied by 1 over n square, 2 over n squared plus 3 over n square, all the way to n minus 2 over n square, n minus 1 over n square. Right? This means this is 1 over n cubed, 1 square plus 2 square, all the way to n minus 2 square plus n minus 1 square. So this becomes 1 over n cubed summation of r square, where r equals 1, to n minus 1. Okay, because again, you notice 1 square, 2 square, n minus 2 square, n minus 1 square. That is the index of the sum. Okay, and then remember earlier the question gave you the sum of r square, right? This is the given information. And now there's n minus 1, right? So remember from the question, sum of r equals to 1 to n, r square is equals to n over 6 times n plus 1 times 2n plus 1. So now your n is replaced by n minus 1. So what you have will then therefore be 1 over n cubed times n minus 1 over 6 times n minus 1 plus 1 times 2 of n minus 1 plus 1. Right? Because now it's not n, but n minus 1. So all the n will be replaced by n minus 1. So this becomes n minus 1 over 6n cubed. The second term becomes n. The last one is 2n minus 1. So this is n minus 1 times 2n minus 1 over 6n squared. Okay, because this will cancel with this. All right, shown. Right, so we have shown the area of the n minus 1 rectangles. Which next, so I've done requirement 2. Next, I'm supposed to explain how the exact value of this definite integral can be deduced from the expression. Right? Now, what do you understand about this definite integral? The integrand y equals to x squared, right? 0 to 1. If I had to evaluate this area bounded by the curve, y equals to x squared, x equals to 0 and x equals to 1, it is exactly this area given by the integral 0 to 1 x squared dx. Right? And how do I obtain this definite integral? From the sum of the n minus 1 rectangles. Right? Remember, this is now the approximation to it. How do I make this the area of n minus 1 rectangles is the approximation of the area bounded by the curve x equals to 0, x equals to 1, as well as the x-axis. Right? So how am I going to make sure that I get the integral 0 to 1 x squared dx? It will then be possible if I start to have more and more rectangles squeezed within the same area, right? Why is that so? Because when more and more rectangles are squeezed, the rectangles become thinner and thinner, right? Imagine for me to fit uh, more rectangles within the same space, okay, compared to just a few rectangles in the same space. When I need to squeeze more, each rectangle must be smaller and smaller in width, right? And there will be such time where it will almost look like a thin line, right, that occupies the entire, or rather it will look like a bunch of thin lines, right, for the rectangles, a bunch of thin lines occupying the whole area described. Yes, and that is actually the limiting behavior of this particular uh, value of A, right, which is going to give me the area under the curve, right? So let's now start explaining. So the area bounded by the curve y equals to x squared, lines x equals 0, x equals to 1, and the x-axis is evaluated by 0 to 1 integrate x squared dx. Now with this integrand, what does it mean? It will be the same as the limit of a when the number of rectangles tend to infinity. Right? Just now I talked about having more and more rectangles within the same space. So I'm saying that let the number of rectangles go to infinity. And I'm now limiting the value of a, which means I'm limiting n minus 1 times 2n minus 1 over 6n squared, where n tends to infinity. Now, you now need to recall from chapter 2 how to find the limit of this expression. So this is actually limit n tends to infinity. Right, one way is for me to expand the numerator. That's going to be 2n squared minus 3n plus 1 over 6n squared. So this gives me the limit of n tends to infinity. 1/3 minus 1 over 2n plus 1 over 6n squared. Okay, why? Because you know the limit of 1 over n to the power of k, where n tends to infinity, is equal to 0, where k is a positive real number. Okay, so then therefore the answer here would then be 1/3 square units. So therefore 0 to 1 x squared dx is equals to 1/3. Okay, so that's how you deduce the exact value of this integral. All right, lastly, we need to show why the definite integral of x squared dx from 0 to 1 is larger than this particular expression. Now, notice that the expression on the right-hand side is exactly a. That means now you're comparing this particular integral with the area of the m minus 1 rectangles. So just now we have already said, right, the integral of 0 to 1 x squared dx is the area bounded by the curve, bounded by these boundaries. Now, what do you notice about the rectangles, right, and the actual area that you're covering? Okay, notice that there are a lot of area, okay, which is not covered by the rectangles. Right, so what can you say about the area of the m minus 1 rectangles compared to the actual area that is covered by integrating 0 to 1 x squared dx? You learn in the lectures that there can only be two consequences. Either the area of rectangles is a overestimate or a underestimate. Right, with so much space not being covered by the rectangles, this is obviously an underestimate of the area bounded by y equals to x squared, the lines x equals 0, x equals to 1, as well as the x-axis. Okay, and that is how we're going to start formulating our argument. All right, so from the diagram drawn previously, right, this method of finding the area of A, right? Because we have defined what A is. Under the graph, or rather, the area of A underestimates the area bounded by the graph y equals to x squared, the lines x equals to 0, x equals to 1, and the x-axis, sorry, there's a missing word, underestimates the actual area. Okay, this word needs to be there. Right, because now it is the area of A versus the actual area bounded by the boundaries described. Okay, and the key term here is an underestimation. So now you need to explain why is it underestimate. Okay, because the space, okay, now notice just now I actually shaded, right, all the empty spaces. Okay, so I'm going to say because the space shaded as shown in the diagram, right, is not taken into consideration in A. All right. Therefore, the area bounded by y equals to x squared, x equals to 0, x equals to 1, and the x-axis, which is equals to the integral of 0 to 1 x squared dx, will be less than, will be greater than, okay, because the actual area is greater than the area, the value of A, which is equals to n minus 1 times 2n minus 1 over 6n squared. That is, integral 0 to 1 x squared dx is larger than n minus 1, 2n minus 1 over 6n squared. Okay, so this is showing what we need for the inequality, but as n tends to infinity, the shaded area that was accounted in A will tend to 0, i.e. the integral of 0 to 1 x squared dx will then be 1/3. Okay, so we don't need this line over here. Okay, so this whole paragraph here will finish up the third and fourth requirement, right, starting from here. Right, from this particular line that is highlighted in blue, right, all the way down to here, right, account for the last two parts of the question. Okay, and that's that for this question.